the way called East Hall, that was originally engineering. So these two buildings were purpose-built as College of Engineering buildings. And that was kind of a radical concept 112 years ago. So this place was finished 112 years ago in 1904. You'll see the plaque out front. And actually a relatively famous architect helped design our towing tank. They've designed other structures around the world. All right, we could probably take a moment and show you guys that as well. We can do waves, big waves in the towing tank. However, you want to measure these waves on a different scale. I guess we can talk another time if you want to do bigger waves in the towing tank if there's opportunities. But this tank we have here in the hallway is, I think it's 165 feet long, and it's a wind wave interface tank. It's designed for studying wind and waves and wave interactions at an environmental perspective, right? And the reason why it's tall and skinny is it gives the waves more of a two-dimensional behavior. So when you're trying to study the physics of something, sometimes it's easier to work with lower dimensional structures before you get to higher dimensional concepts, right? Okay, so we can put wind across this and study how energy transfers through friction at the wind wave or the water air interface from the wind into the water. You're going to see some of that. And we have little wave makers in here too. As a matter of fact, now we have two. We're only going to be using one of them because there was another set of experiments that were done. So let's see, any other questions at the moment? Based on what you know. Okay, cool. Well, let's come on out here and we're ready to run this thing. So we know, what do we have here? So there's a ruler. So what we set up here, I think in the videos we have data sets for you and some video based on previous runs. We gave that to the class, and the idea was those are available and everyone can work off the same set of data. And that was sort of an insurance policy. So if anything ever went fluey here, you could always rely on a standard set of data that we knew was good. But we're going to be able to demonstrate those concepts here. That's my understanding that what you're going to want to do is make qualitative, semi-quantitative visual inspections of the physics here, right? So there's, for length scale, ruler here. For scale, we're generating waves with a wave maker. That's at this end, all right? This is the wave maker unit. It's a plunging wedge type wave maker. It's common when you have this structure like a tank here. There are other types of wave makers, so this is going to plunge up and down, and it's the change in the depth per unit time, or change in the volume immersed in the water per unit time that generates a pulse and sends that downstream. You'll notice that it has a flat back here, and what that'll do is, since it is flat in the back, no energy gets generated in this direction. That's why it works really well in a tank that has a structure on the backside. Otherwise, if the other kind of wave maker that's popular is a flapper. It's probably much more common, but then you have to have structure and space behind it to absorb the energy so that you don't get unusual frequency waves generated, right? So we use plunging wedge type wave makers. And up here, all this gray structure, this is a set of baffles that we pull air in across through here, and it vectors the air in a nice laminar set of flows down the tank. This tank has glass plates all along the top except for a couple spots. Got them covered in different ways with instrument penetrations and whatnot. And there's a great big fan down at the other end. So that at the other end, it's sucking in, right? Great big blower fan, sucker fan. It's drawing air in from this end. And so the air has an opportunity to work along this entire length between the exit here and the entrance to the fan down there. So we have that frictional effect of wind working across the surface of the water. What do you call that? Oceanography? There's a name for it, that length. It starts with an F. That's not a bad word.
Fetch.
Fetch. Yes. Okay. Very good. You're listening. All right. We didn't even pay you to do that. So yeah, this is the concept of fetch, and if for a given constant set of wind conditions, the longer the fetch, the more time, more contact there is between the wind and the water. greater opportunity is to impart more energy into the water. For all those things, right? And so more of the bigger waves that are produced by the wind, probably going to be on the order of a third to half the way down. That's where you're going to see more of that action. Whereas from the wave maker, they're going to be moderately uniform. Some of their higher frequency conditions will dampen out by here, and they'll be uniform from here on down. But you guys will have a fairly long section that you can look at. So, what kind of conditions do you want to see first? Wave maker or?
Usually the low wind and then the high wind. Just going in the order of our questions.
We'll do that. Hey, gents. Let's operate some equipment. So, here are two of the other engineers that work here. Jason Glendoff, Brian Cragen. We've got some names. Do we have that plugged in and turned on here?
Yes. Right.
Okay, so we're going to start with air, okay? So, I think you guys, you need to, we're going to have some information that's going to show up here on some screens. So you're going to want to record, or you want at least a general sense as to what the wind was, right?
Yeah.
I think we have this calibrated so you'll get a wind speed. So in here, about the middle of the air column, there is a pitot tube with a calibrated pressure instrument. So we're going to give you the nominal wind speed, at least at that point. And it should be fairly representative of what the wind is in that cross section. When you get really close to the walls or really close to the top and bottom, it may degrade a little bit because due to friction, but that'll be a good representative sample. The wind is, and I think we have an instrumentation system here, and it'll read out in meters per second. So you guys can write down what that nominal wind speed is, okay? And we're going to run our blower system at only like 25% and then 50%. And it takes a little while to get some steady state conditions. I don't know, on the order of 15, 20 seconds, something like that.
Doesn't take too long. Yeah.
Not too long.
Talk about
But you'll see.
tape markers.
Yeah, let them know there's tape markers. There's some down there for scale factors. Oh yeah, here too. Cool. Yeah.
So I believe you guys are supposed to take measurements at the beginning of the wave train, the middle of the wave train, and about the end. So there are markers down at that end. Waves will be progressing this way, so you guys have already mentioned that.
Yeah, I'll let them know we're going this way.
Okay.
Sweet.
Down there's the beginning, this is about the middle, and down there's toward the end. We can't go all the way to the end because you'll get reflecting waves and those interfere with your waves that you're supposed to be paying attention to.
So do your Leonardo da Vinci thing and observe nature closely,
you're
right?
getting and Brent's going to grab a meter stick.
And make sure you guys are walking up and down to see the different areas. We have 3 boxes to draw in.
So we have a couple yardsticks and meter sticks we can give you in case there's some spots somewhere along that seem more interesting than where we just kind of not randomly, but just kind of threw some tapes if you guys want to figure out your own.
Yeah. The wind generated waves are not as regular.
Yeah.
Go figure, right? Can you turn that on?
No, I was grabbing the meter stick.
Oh, okay. I think it's been energized, but it's not.
Yeah, it's ready to run.
Cranking. Just go ahead and if you want.
Add an inch to it, that's about what your water depth is. So kind of want to record that so you know what type of waves you're looking at.
Is it different depth from the way down?
We need people with initiatives.
Yeah.
Yardsticks.
Come on, guys.
Take measurements. There we go.
Yeah. This door over here, we're going to need to do.
Oh yeah.
Okay.
I didn't realize you guys were still listening.
She calculated voting.
Okay.
Using inches or centimeters?
Sorry. 21 and 5/8 inches. Plus the 1.
Can we do it in centimeters?
Is there something?
Oh, yeah.
Metric's a lot easier.
Yeah, it'll make it easier for your calculations. Thank you. So add
Not
about,
torturing people with slugs of water.
add about 2.5 centimeters on the bottom of that for the water depth.
552?
Sorry, what was that?
552 millimeters, so like 55 centimeters.
Plus the 2.5? Yeah. So 57.5.
Everyone ready?
25?
Yep.
All right.
Yeah.
You can see it, there's a big black round structure to the side of this where the motor is behind the ductwork there. And they can roll it around the drawing area.
Nothing happened.
Yeah, as soon as you start to see, yeah, there's a vibration of the water surface. And as the dust falls in, you'll see the dust particles take off the water surface. There it goes.
So you guys can walk down to the end and you can see the inception doorways are actually.
And they're 2 feet-ish down, right down here. Oh yeah, look in here, they're fairly regular, 2 feet.
Yeah.
By the time you get over here, they're not almost all the way across. You see, you don't get a full, like, exact exhibit, but three-dimensionality to it. And since there is a flat end to the tank on the other end, eventually what happens is those waves will hit that wall and start to reflect back. So that wave underneath too.
This is.
Yeah.
Sorry, I just did it. I assumed that that's an inch. So I just, it was like 0.5 and now it's like 1. And so I guess height increases as well.
Yeah, because waves that have endings are different than waves that are like open and closed.
So open and close, I guess.
Well, it's just like, we basically just talked about like waves that have an ending. Like hypothetical waves don't have an ending.
Yeah.
Or is it this, the actual stuff?
Water coming out. Yeah, I don't know if it's but
Yeah. Well, keep in mind that the wavelength is from crest to crest or trough to trough. So we're going, so you're saying between two crests is 2 inches?
Some of them.
Yeah. I'd say,
They're not very,
yeah,
Especially the capillary waves, and that is already the gravity waves over there. And if you go that way, it should be zero gravity waves.
but then they get,
They get, I think they get way higher waves than
towards the end of the
Yes. But the wave speed looks like it's decreasing.
The wave speed's pretty constant.
Okay.
Yeah. Yeah, wave speed's
And then
constant.
the height
Changes is the
height is
period.
decreasing too.
Yeah.
So wave speed is pretty constant.
so this will be roughly twice the wind speed that it was before.
And the depth is the same.
Well, as a matter of fact, there are levels of swimming that I try to set, and then you use part of the bed. They're usually like this big.
And those, so we just need to make something that's quite pretty easy to fit in those heads.
Yeah.
You can do a lot more.
Let's do that. Yeah, do you see a little bit? So as we're transferring surface to the water flowing that way, somehow that water is probably it's got to circulate back. So we're getting little localized cells of circulating water as well. Yeah, yeah. We didn't mean to do that. Dust gets in there. We don't know where the dust comes from. We just have mystery, you know. So. Good. Yeah, you're right. But there's a very noticeable difference between these or the 1/4 speed and the double the speed.
Right.
It's kind of neat.
Okay, this is 4.5 hertz. Sees the pulses.
Oh yeah. How cool is that? It's even look like it's moving. It's just like it's dancing.
Yeah.
The wavelength is decreasing a little bit, or increasing a little bit.
It's like
getting
this
more-
is the only one where I felt like the height is actually decreasing this way.
Yeah, I felt like the height was decreasing. I think the wavelength was about the same. How about you?
Yeah, I think the wavelength is the same because it's not that actually propagating.
Yeah.
Yeah. It's just like.
Using sugar up here.
It's so cool.
All right, starting wave. that's much
Why is it like sine wave but not like analysis like this
You
way?
don't want just sawtooth, right? So these waves are sine waves, right?
Yeah, right.
So how you generate sine waves is
Oh.
sine wave motion. If you do sawtooth,
So it's not like the velocity is different like when you.
yeah, it actually follows a true sine, so it'll pattern both the velocity and acceleration.
But this like simulates tsunami, right?
Tsunami,
Oh, it's
Long
different.
wave.
yeah.
So this is still like
Shallow.
shallow.
This is
Tsunami is
This is
shallow,
still
water,
deep water.
miles long.
this is still deep water wave, yes.
Okay.
The class super. And then you want to do 2.5 in the same original amplitude.
Yeah.
Right. Regional amplitude, higher frequency.
Swear it didn't shoot to the bottom of the tank.
I'm sure.
Smooth, I can hear that. It can't go.
The background frequencies are low enough.
You guys want to head that way, or where do you want to stand for this one? Because I'm about to start the next one. All right, everybody ready? All right, here it goes.
You don't necessarily have to be a coupler. You're losing your peak and the energy is collapsing. Yeah, so at this, you're seeing it over here, yeah, you do. Regular, those are nice. And then eventually it's kind of cool, you're seeing really regular waves, and then you see your water there. And it
Wavelength definitely decreased.
Yes.
But then I think the amplitude.
Like, cause here it looks like.
Yes, and here's a lot, I think, smaller.
Oh, from the baseline.